Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. What I hope to do in this video is I hope to introduce you to the idea of vectors, and in particular I want to introduce you to the idea of a vector in the two-dimensional plane, or in R2. So let's go to our tablet and see if we can study that in more detail. So our title here is Intro to Vectors. And vectors, I want to kind of discuss the kind of different contexts in which vectors can be introduced, or you may have seen before. So there are generally three different ways in which vectors can be introduced. And we're going to call them the physics perspective, the computer science perspective, and the mathematician's perspective. Well, you might have seen the first two. You've probably seen the physics perspective, where you think of a vector as somehow some object that represents quantities that have a direction and magnitude. And you may have seen the computer science perspective, where you represent vectors as kind of arrays of data. The mathematician's perspective is one that's a little more abstract, and we'll actually discuss that in more detail probably in the second semester, which is where we study the properties or the algebraic properties of vectors and define a vector as something that satisfies those algebraic properties. So just writing them out in a bit more detail, I said there was the physics perspective, the computer science perspective, and the mathematician's perspective. And starting with the physics perspective, we think of a vector simply as an arrow in space. So that is, we think of it as a quantity or an object that represents quantities or physical quantities that have assigned to them a direction and a magnitude. So a typical example could be something like the velocity of a particle. The velocity of a particle is described by the direction in which the particle is moving and the speed of that particle at that particular point in time, which is, in other words, the magnitude of that vector. So this physics perspective is one that allows us to give us a geometric viewpoint of vectors as simply arrows in space. Now, the computer science perspective is already slightly more abstract, where we think of it as arrays of data. So in other words, if we think of this, we write these vectors as these kind of columns. We can equally write it as rows, it doesn't really matter. And these dots here are just representing some numbers or quantities that I'm going to put into this these square brackets. And this whole thing I think of as the vector, and each of these dots I think can represent certain numbers of objects. For example, I could say one of them is say this one here is 3 apples representing, or this is 4 oranges, or so on. So it's representing numbers of fruit being sold or something at the local grocery. And why that's useful in the context of computer science is you might have already seen in examples that you might have these huge sets of data and you might want to organize them in reasonable ways, and you can organize them in terms of vectors. And you can realize this is actually, these two things are somewhat the same when viewed through a particular lens, that you can represent this vector through its components, and its components picture is exactly going to look like this. But in this situation, it's just going to have 2 components, namely its kind of x and its y component, like so. And equally, you could write down a vector in 3 dimensions, and that would be represented by 3 components. But you see already when we move beyond that, if we start moving to other components, right, this thing here can just be going on for this vector can be as long as we want. That doesn't necessarily have a nice geometric picture. We can't return that back to geometry. So whilst the geometry or this physics perspective is particularly nice and has this really nice geometric interpretation, it has its limitations in the sense that there are kind of more general classes of vectors that can't always be represented as arrows in space. Or at least it's very difficult to visualize them as arrows in space, because you would have to project down from higher dimensions to a lower dimension, like say R3. And the mathematician's perspective, as I said, is rather abstract. In that setting, the mathematician views a vector as an element of some space where you can simply add elements of that space and multiply elements of that space by, say, real numbers. And this, in essence, captures the structure of both of these things. So in both of these cases, I can add those things and I can multiply them by real numbers. And that, in that sense, that's really what a mathematician kind of abstractifies those ideas and calls this thing here a vector space, and vectors are elements of that space. So this is much like how you might say take the number 2. You can think of the number 2 as this abstract thing, an abstract quantity and or object, and we can also represent it in 2 different ways, right? We could think of it, for example, as how it acts on the number line by stretching it by a factor of 2, or we could also think of it how it counts objects. So it can be represented in 2 ways, but underlying the kind of idea of these 2 physical interpretations is some abstract idea, which is the number 2 itself. So this is a bit like this here, where this is the abstract idea, and when we start applying those abstract ideas to kind of thinking about what they might mean physically, we get these kind of 2 different pictures. So what I want to do is I want to specifically focus on the moment this kind of physics perspective that we're going to first define. And we're going to talk about vectors kind of specifically just in 2 dimensions, which allows us to think of them as arrows. And in turn, we will see how these 2 corresponding pictures relate to each other. The mathematics perspective we will look at in a lot more detail in the next semester when we talk about abstract vectors. So starting along that line, how can we define what a vector is then in 2 dimensions? So I'll write our definition. And we want to say that a 2-dimensional vector, 2D vector, is a directed line segment that corresponds to a displacement between one point in R2 to another. In other words, if we shift that up slightly and think about drawing R2, so we can represent R2 in the usual way, but on the X and Y axis, so we're thinking of this thing here as R2. And given some points in that space, so let's say we've got one point here that we can describe as A, and this one as B, so this one is A, and this is B. A directed line segment between them would just be simply taking a particular direction, so let's say this direction, and that's how we represent our vector. So it's exactly as we think of it as an arrow. It's a directed line segment between 2 points in our space. Here we've taken A and we've taken B. And we could equally have taken some other points. Say we could have taken here C and D. And we could have some directed line segments, say let's go in the other way. So that as well is another way of thinking of a vector. So in this 2-dimensional setting, we can really think of vectors as arrows between points or coordinates in the space R2. And maybe we should talk about some notation now, just so we know what all of this means. So we would say that this point here, let's call the point A here, so this point A is what we would call the initial point of our vector. The point B here would be our terminal point. We call the base of our vector the tail, and we call the tip of our vector the head. So that's kind of some notation there. And how can we also write these vectors down? So A and B here now are points in R2. So we sometimes write this vector, say this red vector here, the notation A, B with a kind of arrow on top to mean that we're starting at A and ending at B is used to represent vectors. Or let's say notate vectors. And equally, we sometimes use boldface, but we can't really write boldface when writing here on the tablet. So the notation kind of underlining a quantity is used to represent a vector. So in the notes, I reiterate there that this is written as boldface in the notes, but it's not so easy to write boldface when doing it with handwriting, so we just use an underline here to represent that this quantity is a vector. So this one here explicitly tells you that if I've got some point A in my space and some point B in my space, that this is the vector, the directed line segment, that starts at A and ends at B. So this would correspond exactly to this red arrow up here. And V here is just a quantity that we're saying is a vector, and that vector, we know it's a vector because it's been underlined there. Okay. So let's just kind of do a bit of a recap of what we mean by R2. So recall, R2 is R Cartesian producted with R, which when we write that, that's the set of ordered pairs or two tuples A, B, such that A and B are in R. So these represent the coordinates, the X and Y coordinates on our two-dimensional space. And using these X and Y coordinates, it seems reasonable that we can define vectors for every point in that space. So for every AB, every point in this space, in R2, I can define a vector, namely I could define the vector that starts at the origin and goes to whatever that point is. So that is to say that, shifting our stuff down here, that every point, we'll write as A1, A2, so this is a point in R2, it's in R2. Or should I say to every point, one can assign a vector we'll write it as A underlined to mean that it's a vector, which we write in this square bracket notation as A1, A2. So it has the exact same components here, it has the exact same points as these things, but notice we use this notation with the square bracket instead of round brackets, because here we're representing coordinates in the space, but this thing here is representing a directed line segment. So this is something that has some sort of direction. This is simply coordinates of that point, and this thing here is representing a vector, which are two very different concepts. So that's just an important notational point to make out, that coordinates are not the same as vectors, but we can describe vectors in terms of coordinates. Okay. Now, the next thing we might want to say is, well, we can describe to every point in that space, we can describe some vector, which we describe here as coming from the origin. So in other words, we can actually realize that this thing here is the same as OA. That's what we're defining it to be, where O is the origin. But we could also want to be able to talk about how we can write down a coordinate perspective, or how can we write down this coordinate expression for any two vectors, or for a vector between 2 points A and B. And that is what will lead us to the idea of a coordinate vector of AB. So we know how to write down the directed line segment AB. In other words, if I'm given the coordinates of A and the coordinates of B, I can write down this arrow, and that's my directed line segment. Is there a way of writing this line segment in terms of this notation, in terms of the coordinates of A and B? And indeed there is. So let's go to our definition. And our definition says, so we want to start off with two general coordinates in that space. So let A equal A1, A2. And we can say this is an element of R2. And B equal B1, B2. That's also an element of R2. Then we can say, then the coordinate vector of AB is given by the following. So we can write AB in terms of these coordinates as B1 minus A1, comma B2 minus A2. So that's how we write down the coordinate vector for our directed line segment AB using our coordinates A and B. Again, notice the distinction here between the square brackets, which represent a vector, and our kind of round brackets, which are representing points in our space. And we call these elements inside this directed line segment AB the components of our vector. So that is the terms B1 minus A1 and B2 minus A2, that are both real numbers here, are called components of the vector. This is the vector AB. So we can describe a vector, we've seen here now in this kind of computer science perspective and this physics perspective, one as a directed line segment, and from that directed line segment we can write down it in its component form, and equally speaking from its component form we can write down the directed line segment, right? We can figure out what if we're given this component form, then we can deduce what our points are here and what our points are here, and therefore we can draw an arrow between those two things. Okay, so let's just go back to some notational points, because that's what I've mentioned here in the notes. So firstly, it follows from the definition of R2, so in other words, from this set of ordered pairs, that AB does not necessarily equal BA in general. Right, and that just follows because our definition was it was a set of ordered pairs, that was the order mattered. So in other words, if I had AB and then A comma B and then B comma A, those things aren't necessarily equal because the order matters. In fact, they're only going to be equal if the components themselves individually are equal. And that will lead us to our kind of a definition in just a minute, where we're going to talk about equality of vectors. And also, the coordinate form of vectors may also be written as, we could write it in this column form, which is A1, A2. So this is kind of just a different notation to the one like up there. And we sometimes refer to this one here as a column vector for obvious reasons, and this one as a row vector. Now, for all intents and purposes for now, these two things are identical. You can think of this thing as just the same as this, it's just a different notational point to describe the two things. In reality, they are slightly different. One of them here represents a vector and the other one represents something called a dual vector, but we probably won't talk about that in this course in too much detail. So just to reiterate, this is just a notational point to describe vectors, or at least their coordinate expression for vectors. We can either describe it in this column notation or row notation, it doesn't really matter. You can pick the one that you like the most. Okay, and then there's a kind of special vector that we want to look at now. So we ask ourselves the question, well, it seems possible now in the coordinate form, we can have 0, 0, right? I could just do that by taking the 2 points to be the same. If I take A and B to be the exact same point, then I would see from my definition over here, that I would just have B1 minus A1, but because they're the same, that would be 0. And B2 minus A2, because they're the same, that would also be 0. So it seems pretty reasonable that I can write down this 0, 0, a vector, right? Because we've seen so far that we can write down from directed line segments, we can write down these component or the coordinate corresponding values of the vector. And now for this coordinate point, how can this correspond to a directed line segment? Well, as a directed line segment, this is going to be a kind of line segment that has length 0. Which you might think, well, this is not really a vector, and therefore I can't define it. But indeed it is a vector, and it's such an important vector that we're going to give it a special name, which is known as the 0 vector. So that leads us to kind of another definition, which is to say that the zero vector, again, this is all just in R2, is defined, maybe I should reiterate that, I'll put it as the zero vector in R2 is defined as 0 with the underline, right? So here it represents a vector. In the notes it's represented in boldface, but I've already explained that's not so easy to do, is simply just this thing here. So it is the vector that corresponds to the one that has both of its components of 0. Why is it special? Because what we will see in the kind of future video, that if we add vectors, the zero vector has the special property that it's the unique vector that when I add it to other vectors, it leaves those vectors unchanged. So that's why it's rather special. And then the final thing that I want to talk about is the equality of vectors. So what does it mean to say whether or not two vectors are equal? And what's a little strange here when we think about equality of vectors is, suppose I kind of draw my Cartesian plane like so. Now, it is possible to have that the coordinate description or the coordinate vector of one of my vectors is equal to the coordinate vector of another one of my vectors or my directed line segments, but they're not obviously, or they're not the same directed line segment in my space, in my two-dimensional space. So let's write this out. This is R2. And what I mean by that is, let's take this point A here, take the point B. So this is A, this is B, and we take our vector in between. Now if I take another vector, C and D, also I take a 2 more points C and D, and I draw a vector in between them. Now if this vector here is parallel to this vector, it doesn't necessarily look like that in that case, but that's because my drawing is not so great, then you would find out that the components of those two vectors are in fact identical. So if it's parallel and the lengths are the same, then the components will be identical, but it doesn't appear like these two vectors are equal, right? Because they're not the same directed line segment. So let's just see this with an example. If I write out some explicit values, and these are in the notes as well, if I say let A equal the point 3, 1, B equal the point 6, 3, C equal the point -4, -1, and D equal the point -1, 1, then what is the vector AB, or the directed line segment AB? Well, how do I do that? I know how to compute that. I take the first component of B, which is 6, and I take away the first component of A, which is 3. I use my square brackets because I know this thing is a vector, so that's 6 minus 3. And then the next one, I take the second component of B and take away the second component of A. It's 3 minus 1. In other words, the overall vector is given by 3, 2. Now what about CD? In this situation, I take the first component of D and take away the first component of C. So that's -1 minus -4. So I have -1 minus -4. And for the second component, I take the second component of D and take away the second component of C. So that is 1 minus -1. So computing that, we've got 4 minus 1, which is 3, and 1 plus 1, which is 2. So we see that the components of these two things are the same, right? But these two things do not look like the same directed line segment in the space. So how do we get around this? Are these two things equal? Well, we define them to be equal if their corresponding components are indeed identical. And we'll see what that allows us to do is that allows us to realize how two vectors are equal in this geometric picture. So that leads us to our kind of next definition. To say whether or not two vectors are equal. So we let our first directed line segment be written in its coordinate form as A1, A2. And let's call this CD equal B1, B2. then the vectors are said to be equal if A1 equals B1 and A2 equals B2. In other words, indeed, these two vectors here are equal. So how does that correspond to our geometric picture? How does that kind of resolve this round here? Well, if we define that as our definition of equals, what that means to say is that two vectors or two directed line segments are equal is if we can take this, let's say we fix this vector here. And if we can take this vector and transport it along or translate it such that it keeps it parallel as I translate it along, and I translate it so it lies on top, directly on top of this vector, then that means that the two vectors are equal. So in other words, two vectors in our space are equal if we can parallel transport them onto each other. And what we can also realize then is that there isn't necessarily a unique way of just writing one of these vectors. We can put our vector anywhere we want within the space, or at least draw it as an arrow in that space by just parallelly transporting it around the space. In other words, we just translate it, keeping it parallel to the initial vector. So we could write this vector as this one, or equally speaking, we could write any vector as this vector by just shifting it. So now its base, the kind of point here, its tail now lies at the origin, and its head now is just extended outward. So that would be the exact same vector if we just transported this one along, translated it, keeping it parallel, not changing its length. So now its base lies at the origin. That would also be the same vector. So this is another way in which we can visualize and be particularly useful for when we're thinking about adding vectors. And we already saw this in some setting when we talked about adding complex numbers, because we thought of them in some sense as vectors, and we saw that we could translate our vectors freely around our space, providing that we didn't rotate them in any way or stretch them, that we could represent that vector at any particular point so we can kind of parallel transport it around the space. So I think that's where we're going to conclude the video. And in the next video, what we're going to do is we're going to talk about how we might add vectors. And well, we're not going to talk about how we're going to multiply them, because it's not really possible to discuss a structure such as multiplication of vectors, but instead a structure known as scalar multiplication, which is equivalent to kind of stretching or squishing your vectors or the vectors by some scale factor. So as always, I remind you to read the notes after or before this video and to attempt any problems in the module handbook pertaining to the material discussed in this video. So thanks very much for watching, and see you in the next video.